go on for 1 hour, 1 hour 10.
Exactly.
10 to 3 with activity.
Yes. Okay. So it's just to complete the idea. I mean, Wednesday, hopefully you guys got the picture of what we're doing here, which is we study a slightly different problem than the bound case, which is the scattering now. And we wanted to compute an impulse, say of particle 1, where we integrated, and there's some sign convention, the interaction action with respect to x mu. And there's a tau dependence, and this is particle 1, and then we integrate in time. Then we obtain this interaction Lagrangian, or action, which is a function of the x's, and the x's are these guys, which are our sources for all the gravitational field that is produced, that binds the system and also radiates. We say we obtain this guy by integrating the total action that depends on the metric degrees of freedom and the sources are the ones that are going to survive. And this action does two things. Once, it gives us the equation of motion, because there will be a p dot that we need to solve for up to a time t, from which we're going to get the deflections in the position and the velocity up to a time t. And here we had to be careful, because the integrals that we solve, there will be integrals up to a time t. And remember that we can put a step function there if we go up to t in some t prime variable. And that's what's giving us this type of linear propagators. This is what I wrote last time. This is the deflections away from straight motion. So we look for solutions in which the motion is straight up to corrections. So we say we're going to look for solutions of x, 1. This has no mass here, plus some n-order deflection. And then we sum in n. This is the guys that we can do the Fourier transform, and the sum of those integrals when we integrate in time. Remember, give us the delta functions, but some of the equations of motion will be integrated up to t. So some of these deflections will depend on linear propagators. And why do we need that? We need that because here we compute this to an n order in G, but we also need to plug the deflection. And last time we had here the 3-level exchange will give us the 1 pm on the unperturbed trajectory, but then we need diagrams like this and an iteration there to get the 2 pm. And that's what started getting us these deltas of the word lines. We start getting, for example, if this U1, this is there's a U2 down here, and then we start getting here, this is L1, then you have, say, L2, and then, for example, L2 minus Q squared, and here we had 2 or 1 in the one loop, sorry, because we have 2 directions that we had to disentangle. The delta P mu will have something in the B direction, and something in the U directions. And then you just do the tensor reduction. You just multiply and get the scalar integrals, decompose in this way, and then you use that B dot U is 0, and that U squared is 1. And then when you multiply, you'll see that you're going to get the delta P mu is going to depend on some momentum for like an L mu, And when you do it into the u's, you're going to see that LU is going to cancel one of these guys. So for the velocity, you're going to end up with an integral like this. For the B direction, you need this integral for the deflection. And for this guy, you will need an integral like this. Because there is an delta, this is the standard D3 integral that we love from potentials. And you have to be a little bit careful with the U integral when you do the L0 integral here. But that's in the U direction, and if I'm doing conservative, I don't care about the U direction because the B direction determines everything, because the leading order is in the B direction, and then conservation of momentum, and P squared will give me this. I can bootstrap from here, because P plus dP squared is P squared. So it's very systematic that the B direction is the only thing you need for the conservative part, and if you think about doing an action from which you take a derivative, like the radial action, and then you get an angle, is basically what comes from this part. So it simplifies your life to get a bunch of scalar integrals, which is ultimately what I need to do. And then you see when you do dot, 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 that what you get is a bunch of propagators, there is a transfer momentum, and there is a bunch of linear guys. So we start getting more delta L2 U2, and then you have L2 U1, and so on. So you start getting more things. And the state of the art right now in solving these integrals is not brute force like we did at 2 p.m. It's using this idea of rewriting this in terms of masters and doing this transformation. Oh, I think I wrote it down this time. What the x is to solve for the integral. So the idea is this integrals can only depend on U1 dot U2, which is gamma. Remember, if you know the integral, the solution to the integral, you already got the dP. The dP just depends on gamma and gm over v expansion, and that's what the angle is going to depend upon, because from this dP we're going to get our angle as a sum in the PM expansion. You often will get this 2 just for the fact that the sine chi over 2 is what the dP over P infinity is, as we saw last time. And so these guys are going to be just a function of gamma. And that's good, because if we know that guy just a function of gamma, we are done. And this is what I'm going to tell you today. You're done for the unbound case, so how do you go to the bound case? But that's basically what we need to do, is calculate these integrals. These integrals depend on these factors, so what we do is we write these masters. We get a vector of integrals in these masters, and then we go to this variable x, and that's because most of the time there are square roots, and that rationalizes the square root. So gamma in terms of x is 1 plus x squared over 2x, such that the square root, which is the problem, which is this v infinity factor, which is the velocity infinity, becomes 1 minus x squared over 2x. So we don't have to deal with square roots, which is part of the problem. That's the only reason for this x variable. And it's also the reason when you solve this as an RJ that you get log of x, but then you get the arc sinh when you go back here, because you know that you can write the arc sinh in terms of logs. The arc sinh minus 1. Yes. So then you have a matrix, if you do it in d dimensions, and then you have to solve this, and then you get the f's that are going to depend on x and epsilon. And the point is that it's up to boundary conditions, so up to boundary conditions that we take in the post-Newtonian limit of gamma going to 1. This x is between 0 and 1. 0 will be infinity. And these integrals then become these integrals in the region in which we can use post-Newtonian expansion. And then we use the potential modes that give me, for example, this 2 PM integral that I discussed. But there will be also radiation modes. At some point, we're going to have integrals like this, where there will be radiation. This will be at third post-Minkowskian order. And if we do in the Feynman boundary conditions, then there will be an imaginary part, because it will be a square of an optical theorem. If we were doing the retarded calculation with retarded boundary conditions, we will get an answer for dP that would include all the radiative effects. Then you go to 4 p.m., and you start getting stuff like this, and this is our tail. And this one has both dissipative and conservative. And then it becomes real because this one will be imaginary for Feynman, but since you have two guys, you can make real, and there is a choice of symmetric propagators. There's a whole discussion about what is the conservative part, but if you're doing the retarded propagators, you do the full thing, then you get the full tail contribution, which appears at 4 p.m. at G4 for the first time, actually G4B squared. And this is generating a little bit of a problem. When you look at the solutions to these differential equations, that you do the method of regions, it's all good up to 3 p.m. And in fact, at 3 p.m., that's when you get the log of x at 3 p.m. Then at 4 p.m., if you do everything with the potential regions, so all of these potentials in the boundary conditions, then you start getting here the dialogues of x, x minus 1, and a bunch of combinations, and then you get the elliptic integrals, the E and K's, and of the first and second kind, all from the potentials. And then when you go to the radiation, you start getting dialogues and other stuff as well, but you also get something, which is a log of 1 minus x squared, which becomes the log of the velocity. So you get a log of infinity. And where did this come from? Well, this comes because when you do the method of region, the same way that it happens in an RGR, you get the potentials that give you an infrared divergence, and you get the radiation that give you a UV divergence, and they cancel out. But they cancel out in a very peculiar way. There will be a pole in dim reg from the potentials, and there will be a pole also in the radiation. But the radiation will come with a rescaling of the momentum that picks up these velocities, because remember, in the radiation region, the K goes like VV versus the potential that is quasi-static, that we could span the K zeros, and that in the measure will pull out a V to the 2 epsilon, and that will give us this log at the end of the day. So it's really attached to the fact that we have radiation. This is like the beta log that we have in an RGR. In an RGR, what happens is that this diagram becomes something like this. And then the potentials have this divergence when you do the calculation that at G4, there is a pole, which was the 4pn. And then the tail has also a pole, and they cancel. The difference is the way they do this calculation. There is a log of R from the potentials in the diagrams. And then in the tail here, there is a log of omega. You combine these two, you get the log of omega R, and that's your V. Here we get the V directly. And there is no ambiguity with the divergence. The divergence cancel out. Better do, because I'm going to unobservable. Whereas here, there's a choice of what this R is when I compute potentials. So it's a little trickier. Of course, it's consistent. And to be consistent, actually, there's something very nice, which is that this you can show universally that goes like d omega log omega, which means for this to pair up the correct way, the potentials that you get from the diagrams, this log of R has to go like d dt, such that then you see that you get the log of V, and the log of V is going to be multiplying something, because you're integrating, it's multiplying the total radiation because you're integrating this guy. And that's very nice, because the coefficient of the log knows about the emission. No, I don't substitute. I get that. I can show that the Hamiltonian from the potentials, the log piece of the Hamiltonian that comes with the IR pole, looks like this. There's mu on both. Yes, there's a divergence, so there's mu and mu in the prefactor. Well, there are G's. I think it's G d dt in the Hamiltonian, and there is what is it, GM? Yes. No, this is the same when such that when you compare with the tail, this guy goes into this guy to give the log of V. It's exactly the same. It better be, because the poles also have to cancel, right? You can check this explicitly in the... We can even check in our calculation of the 4 p.m. that you can really see that this is, but it's a different gauge. For example, Thibaut Damour and company did this in ADM, and they get here this guy in ADM, which is different than our guy in harmonic. And that's why this piece is gauge dependent, whereas this piece is gauge invariant, which is very nice. So when you put them together, of course, the observable that you get at the end, which is the integrated thing, will be the same. But this piece and this piece, since you can move R, the log is going to come out the same, but the constants that come out with it are gauge dependent. Yeah. But there's Q3, Q3 here. See, in the tail, is Q3 omega, Q3 omega. This has to be the dt, because otherwise the poles don't cancel. And it comes out to be the dt. It comes out for us, and it comes out for the calculation of Thibaut and company. But this is just getting a little bit ahead of ourselves in the sense that this is how NRGR deals with the tails and so on. But if you have never seen that, this theory, the post-Minkowskian expansion, is already telling you from the solutions, when you look at the boundary conditions of the differential equations, that you get the radiation modes contributed, the potential modes, the divergence cancel, and you end up with the beta logarithm, which happens to have the proportionality, which is exactly the flux emitted at the previous order from the leading tail. There are higher order tails as well. The coefficients of the higher order tails, we don't know. But for the leading tail, this is the case, which is very nice, because that also gives us for free this delta E. And also the method of region is telling us how do we rescale the momentum in which we get these factors of V that tell us how many radiation modes you have. Actually, you end up with 2, so there's a 4 in this calculation. There's an issue between boundary conditions, retarded and Feynman, that I'm not going to get into. Most of the calculations have been done with Feynman, keeping the real part, and the tail, in that case, will give you a conservative piece. And you can see that from NRGR as well, if you have any familiarity with this type of calculations, because here is the QMMQ coupling. And this guy, if you do it in Feynman, then you get an I pi difference. If you do it with the so-called in, in which you have to double degrees of freedom and use retarded, then you get I pi sine of omega. And that difference is crucial because this picks up an imaginary part that knows about the cut, that knows about the emission, and this picks up a real part, which is the radiation. It's also nice because Feynman, we have a cut here, so you know that the imaginary part of this guy will have to be the emission. And because the imaginary part of this and the pole come from the same thing, and it's the same either retarded or advanced, because the only difference is whether you put the I0 there or outside, that already tells you, the optical theorem is already telling you that the overall coefficient has to be the energy, which is very nice. So without any work, if you had ever seen this calculation, we knew already that the coefficient of the law had to be the energy. And we proved this to all orders. It was also observed by people like Ricardo and so on. We proved this at all PM orders explicitly because it's actually very simple. So great, so that reduces the problem. Just compute the integrals, solve the differential equations, do the method of regions in the boundary, extract the contributions, and isolate, say, if you're doing conservative, you're doing symmetric boundary conditions, what your angle, conservative angle is. You're going to have contribution from potentials, but also the radiation like these tails. You can do the full in, which means retarded, and then you get the full thing. This guy will also contribute, but this one will also contribute, obviously, because you also dissipate. All these diagrams in post-Minkowskian have a counterpart in post-Newtonian. Why? Because when we do this boundary condition, we're basically doing an RGR. And how does that work? Well, it works because the potentials are shrunk. That's what NRGR does. It shrinks this to a multiple. So that's the radiation guy. This shrinks to a multiple. It's talking to the mass of the system. And all this kick of the scattering, if you want, is all in derivatives of Q. When you compute this diagram, you end up with a Q3. That Q3 will have an acceleration, and that acceleration will be GM over R squared, and that's equivalent to putting precisely the kick in the calculation. So all of this matches into each other very nicely. It just redistributes the way we do the calculation. In NRGR, we work with queues, we compute the action, and then we solve for the queues and put dots. Here we did that already, and then we just go ahead and compute the final observable. We already replaced the queues with the accelerations and the potential part of that force. And that's already in this diagram. Now, it turns out that there is a little bit of a catch, which is in NRGR, we do it the other way around. In NRGR, we integrate the potentials first, we get the queues, and then we do this one loop or two loop in the tail. Here, actually, it's convenient to first integrate the radiation modes. If you look at a diagram that has a radiation mode, then you go ahead and integrate the radiation mode. After you integrate the radiation mode, then you're going to end up with a potential integral, and then you do that one at the end. It's just computationally easier. So we shrink kind of in the opposite direction. It's easier to do the radiation because the integral is a whole integral now. We open this up into a whole integral. It's easier to do the radiation part of the boundary condition and then the potential than the other way around. But the idea conceptually is the same. If we knew how to do it, we could do it the other way around too. It's just that we have these integrals are known, and they go into the type of integrals that one can parameterize and do. In fact, the Feynmans are harder than the retarded. The retarded integrals, they turn to be easy because the I0s are inside, and that makes it easier. So very good. So that means that we're going to end up with an angle. That angle is going to depend on gamma. And right now, the state of the art of the angle is 4 p.m. for conservative and dissipative full. And there's also a spin orbit that has been computed and a spin-spin. And at 5 p.m., the 1SF conservative is known. And 1SF is, remember, the factors of nu that start appearing already at 3 p.m., also appear at 4 p.m. At 5 p.m., you're going to get nu and also nu square. On top of this 1 over gamma that we discussed, there are these other guys. This one, with Feynman boundary condition, is what is being done. Even in velocity, it's not complete. There is an odd in velocity, conservative 1SF at 5.5 that was not calculated to all PM orders. The PM version of this, the PM version of this has not been done. And that's because this will involve the tail of tail, whereas this is the tail. So what's been done is the tail, but not the tail of tail. And none of these nu squares yet. And here already, and this takes me to the second part that I wanted to tell you about scattering. This already tells me that we have a problem, which is nice that we keep on going, don't get me wrong, but at some point we have to be careful because these logarithms, which are there, which come from the tail type of diagrams, which have this log of omega, are introducing a bit of an issue. In our theory, is that if you go and Fourier transform the action, this is non-analytic, so you get a 1 over t. And that means that your Hamiltonian is not local in time. That means that the tail Hamiltonian associated with this tail term, which is this log omega, when I go, my effective action has this log omega. The dE dt log of r is completely local. No problem. The log omega from the far zone is what creates a problem because then it has a Hamiltonian. If you translate back into time, so the action from that log omega will be something like this. And another one, yes. The Hamiltonian is what I wanted to get. The Hamiltonian, which is the 1 dt prime, is non-local. And that means that it depends on the trajectory. And therefore, the idea that originally people use, which is a good idea, and also what we did, which is if I can get a Hamiltonian out of this that reproduces this angle, I call it hyperbolic, but if this guy were local, then I can use it for elliptic, as long as it's local. But then what do you do when it's non-local? Okay? So what I'm going to tell you is like, first of all, I don't want to do this. because I have a beautiful gauge invariant angle, and I'm going to slaughter my theory by constructing a Hamiltonian. I don't want to do that. I want to go straight from the observable to the observable, unbound to bound. That's number one. Number two, we're also going to have an obstacle when we do that, the same obstacle that we have because there is not a local Hamiltonian, and that means that we need to do something with our dictionary. This is what mostly amplitude people did. What we did was relate chi to the radial action for bound. That would be the boundary to bound dictionary. That if you give me chi, I give you the bound radial action, and from here, all observables. But this also has a problem with the non-locality. What about the non-local? Also, I'm going to tell you, not only the conservative part, also the dissipative part, which is we can relate the total flux of hyperbolic to the total flux of elliptic through the same dictionary. And that allows us to read off a flux, which we can use then together with the binding energy that you get from here. From here, for example, you get the binding energy. From here, you get the flux. And therefore, you can do adiabatic waveforms without gauge-dependent objects. If this non-locality were not there, I could construct adiabatic waveforms without ever seeing a Hamiltonian, a coordinate, a gauge, nothing. Because I know how to go adiabatic waveforms in the sense that I know how to construct the binding energy of the system from the angle through the bound radial action, and I know how to compute fluxes from the flux in elliptic, from the total radiated energy that I can match to a flux into a flux here. And then from flux and binding energy, we can get the phi, so d omega dt. So d omega dt, and from here, d omega dt, and from here, the phase. I don't get the radiation reaction force. For that, I have to be a little bit more careful. I can also map the angular momentums, and then I can try to, if I were able to compute this, to actually get the radiation reaction force. Because for the radiation reaction force, this would be dot V, but then R cross F, I need both because I have two components. From here, I get only one component, so I can only get a flux. If I want the force, I need dj. But if I have this, then I can construct the force. And then I can even do the waveforms without even having to average over orbits. There is a caveat here, which I can discuss later. But there's a much more important caveat, which is this all fails, because all of this works as long as we have local interactions. The moment we have no local interactions, when I do all of this, I'm going to land, for example, in a binding energy of the bound case that is not going to reproduce the correct elliptic bounding energy. Why? Because it has all the potentials, so those are local. It has all the logarithms. All the logarithms are actually universal. So the log of V will come out right. So here, local plus log. Good. But there are non-local constants that appear from integrating a non-local Hamiltonian. You will get a log plex constants. And all those constants, they depend on the orbit. Those are the non-universal parts. And that's you need to compute. And what we did recently is remove them. We recently, because we had that problem of the non-local tails at 4 p.m. already, and that's also at 5 p.m. This has not been done at 5 p.m. yet, but at 4 p.m. we can remove the how. Well, we go into the universal part of it. We know that the tails will have this structure. We know how to construct this guy. We just multiply by a logarithm. But this logarithm is important to identify where this omega is. This omega is the omega in the center of mass, so you have to multiply by k dot u center of mass, and this introduces mass and makes this calculation a little bit more complicated. It's not just a simple gamma dependence anymore. There is also mass inside there, but it's a simpler calculation because this guy, I need that lower g order because there is an overall g. And therefore, I can construct this guy. I can just multiplied by the log of k U center of mass. So I got a gauge invariant quantity that I can calculate, and it will give me the non-local part of the angle that I can just remove. This is not how it's done usually in PN. People also remove the log of R. But the log of R is local. I don't have to remove it. It goes for the right, but it's a logarithm. And if you're going to construct a non-logarithmic local in time part, then you might want to remove the log of R. But removing the log of R is gauge dependent. Therefore, we didn't do it. We just removed this part, which is gauge independent. And therefore, you can construct an angle now that has a well-defined local and a well-defined non-local part. This, we don't know. And this, we go through all of this. And it's very nice because it carries all the resum velocity parts. You have to do something with this. We go back to post-Newtonian and we put them back, but evaluated on post-Newtonian calculations. So we compute them in a bound orbit up to, and it's easy to do because now we know how to do them. Actually, they're known up to 6 post-Newtonian order. So we get a full local plus a 6 post-Newtonian bound version of this. So our bound radial action is full local plus a 6 post-Newtonian version of the non-local part, which is extremely good in comparison to everything that has been done. In fact, there is just G5 pieces missing that I can put, and if I put the G5 pieces missing and a static G6, then we get the most accurate that has ever been done so far in PM hybrid two-body problem solutions. Yeah. The Hamiltonian has these terms which are integrals in time, and you have to do something with those. Because when you evaluate them, you can make them local. You can make them local by evaluate them in some post-Newtonian order. But they will depend on the orbit because you have to do an integral. Whereas if you have a Hamiltonian that's just 1 over r, it's obviously independent because it's a local interaction. This interaction tracks the orbit, and therefore it's not going to be the same for one or the other. Because the logs are universal, then the logs come out the same, but not the constants that appear when you do the integral. So the Hamiltonian has a lot of, for example, you see here that if I do for the integral in scattering, I do an integral with a log with a continuous frequency. And then I get something. I get a log of x and numbers. In the bound case, the spectrum is discrete. So forget about elliptic, just circular. Then you get 2 omega, 3 omega, 5 omega, all the multiples. So you get log of 2, log of 3, log of 5, blah, 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 blah. All of those will contribute to the bound case that I cannot possibly see from the scattering calculation because I'm integrating a continuous function. The spectrum is very different. Now, luckily, if I don't put the log, when I integrate this, I get the delta E, and that I know how to map. What I don't know is when I weight each mode with this log. And then I start picking this extra log of 2, log of 3, blah, blah, which I cannot reproduce. Also, there's a gamma Euler integral, which appears in the tail, that disappears in the angle, but it's there in the binding energy of the bound case. So you also see that even the non-transcendental numbers don't match. So there is no way to map the angle to a bound observable unless you remove those pieces that are very specific of the bound case. And therefore, we remove the pieces which are specific of the unbound case and we put them back for the bound case. Now I say, but why are you doing that? Well, because the local is the hard part. The local is the potentials, all the tails, local part, which I resum.
Non-local plus a local is still non-local. How do you know?
I know local plus a local.
Non-local plus a local is still non-local.
And if I remove this, my angle is local. So I go through my map, and I'm missing the non-local part of the Hamiltonian that I can calculate explicitly up to 6 post-Newtonian order. Exactly.
Yes, but the non-local is always ambiguous.
No, this is gauge. No, this is gauge invariant. The non-local part of the angle is gauge invariant. Of course, I can add and subtract stuff to this. But why would I do that? Because when I go to the bound case, I'm going to add and subtract the same thing. So that would be silly. All I need to know is how to compute this for the bound case. That's it. Yeah. Yes, here there's a nu square. 5 p.m. nu square. 4 p.m. nu determines everything, modulo this 1 over gamma, right? Because the angle, remember, always gets this p infinity downstairs that gives you the gamma. So now, in the remaining, I will tell you, so this is the idea, right? How do I map? Well, I need to remove the pieces that I don't like, and I need to put them back. That's how we know how to do them. Unfortunately, we don't know how to calculate this in post-Minkowskian. I don't know the bound version of this. Why? Because that thing in post-Minkowskian gets all G orders. When I put it on an orbit that knows about G, because the orbit itself depends on G, it's a circular orbit, then each G will contribute. So we get corrections to the radial action or to the Hamiltonian or to whatever observable you want to whatever object you want to use for the bound case. That depends to all orders in G. So it's not clean. Unfortunately, we don't know how to resum that. It's very difficult to imagine a resummation of that, but that's an open question. What we can resum is the local part, and the local part goes for the right. And we checked, actually. We computed this. We check explicitly that our Hamiltonian, we actually did it through the Hamiltonian because it's what people did. We have a gauge invariant part, but then we decided also to compute the Hamiltonian. The Hamiltonian that we have, the full Hamiltonian that comes after combining everything, agrees with the full EOB Hamiltonian at 4 p.m. at G4 and includes also all the new terms of the velocity. So it goes beyond what it has been done so far. So it's perfect match, which is very nice. Okay, so now I'm going to tell you how we do this B2B map, and that will more or less tell you how this works, and you'll see where it fails, and then how this is done to deal with the fact that it fails. It's like identifying in a gauge invariant ways the terms which are not local, remove them from the unbound case, compute them and remove them. That's easier said than done. That's a hard calculation because of the new scales in the problem, because of the mass in the log that was not here before. So it's a 2-scale problem versus a 1-scale problem. And then put them back. Now there's a limit in which you expect that these effects will go, which is the large eccentricity limit. So we compute them in a small eccentricity expansion, but if you compute them in the large eccentricity expansion, you start approaching the limit in which those are the same guys that you get from scattering. If you do a hyperbolic motion, then they should be almost the same. So there is a notion in which the hyperbolic Hamiltonian also works if you have large eccentricity. But for most of the observables that we have right now, which are for small eccentricity in LIGO, you cannot use that hyperbolic Hamiltonian. You have to do something, and that something is what we have done. Damour and Bini and Geralico, what they did is because they do it differently in their approach, they don't subtract just this, they also subtract the log of R. They took our result, they added a log of R version to 30 PN order to contract their version of the local, which is accurate to 30 PN and G4. Ours is accurate to all orders in velocity. But I keep the logarithm there. They don't want the logarithm. It's just, okay, it's a choice. I don't know why they want to remove the log. The logs are universal, beautiful. They go for the right, and I get a PM exact coefficient, PN exact coefficient. But okay, they do it differently. Maybe because the way they map into the EOV Hamiltonian after they get this thing subtracted. Okay. So how does this work? Let me just tell you in whatever I have left how this map works. I already give you some basic idea. Which is, if we write a Hamiltonian, you say you have a local Hamiltonian, it will be an expansion of 1 over R, and the Hamiltonian depends on R and P. If you solve for P, then you can have an expression that I like to call the impetus formula, also because this is what was originally related to the scattering amplitude in the original basis, which is just inverting this Hamiltonian, but it's actually the right one. The Hamiltonian is the hard one. The Hamiltonian is not the natural one. The natural one is this formula, and then you can obviously invert it to get the Hamiltonian, because you have a momentum at infinity, and then you have a sum over some coefficients, and if I factor out this guy, these coefficients, we denote it as Fn's. And there is a one-to-one map between the chi-n's and the fn's. And this can be seen in many ways. The natural way is to construct the radial action, which is proportional to the integral of the momentum. And if you do the unbound case, then this is our guy. And PR, here, if you do PR, you have to remove the angular momentum, the P phi, right? And then you integrate the square root of this. And you can actually do that integral. You can do this integral by deforming contours, and you can get a solution that will tell you, once you do the angle, well, you have a leading order, because if you do the leading order with the 1, you get the pi over 2. So just the corrections, which are the ones that I care, the interactive part, is proportional to the derivative with respect to j. Obviously, there was the leading order piece that you don't care. So you take a derivative, you get the angle. So if you know how to do the integral, you take derivatives, you get the angle. So you know this gives you hypergeometric functions, so you can do them, expand in PM, and then you get coefficients of the angle versus coefficients of the fn's. So the chi1 is proportional to f1, the chi2 is proportional to f2, but then the chi3 becomes more complicated. The chi3 becomes f1 cubed plus f2 f1 and some f3 with some coefficients. And dot, dot, dot. So then you start saying what I was originally mentioning. If you know an angle, you know a Hamiltonian. Yes, essentially this map. Because if you know the angle, you know the momentum through this relation. And if you know the momentum, you invert and you get a Hamiltonian. So there is a way to relate the F's and the C's. The problem is that this has to be done iteratively because P itself depends on the F, so you have to take derivatives. So the C coefficients of the Hamiltonian, often the Hamiltonian is written as something like this, but if you go to the center of mass relative momentum, this will be just P, and then plus a sum of some Cn's divided by Gm over Rn, starting from 1. Inverting this to get this means that you need derivatives of these F's to get the C's. So it's a mess. The Hamiltonian looks awful, even though these F's are beautiful. The F's are directly extracted from the physics, like the chi's. And now that I know the F's, by the way, that also resums everything, as I told you, because if I know the F, I can put it back and compute the full angle, and therefore I have a resum version of the angle, because you start seeing here, for example, the F1 theory, which is Newton, has a chi3, and has a chi5, and a chi7, right? But it's just the F1 theory, it's just the 1 over R potential, but it has a lot of terms. So that means that if I extract the n order from the n order angle, I have an n order p squared, I have an n order Hamiltonian that is going to give me all the chi's, not just the chi3, it gives me everything. I'm missing the fn plus 1 piece, of course, but I get a lot of them, all the chi's up to that order. And that seems to be very good in matching numerics. So that's a very good resumation. It has nothing to do with EOB. It's just what we call Fiercer resumation, because Fiercer was the one to realize how to invert this without having to do this integral. He found a way to relate the angle to the momentum. He realized that essentially the p squared was proportional to an integral over the angle, rp squared. From Rp to infinity, and this P is divided by P infinity. It's solving the inverse problem. So how do you get this guy here? You start taking derivatives and invert this condition, and then you get this. You still need to do an integral, right? This guy just did the inverse problem. So you know the angle, you know the P, and now here it's very easy, right? You span the chi in PM, you do these integrals and bring them down, and then you get these guys. And this was done by Firsov. He didn't do this, he did this, because he wanted to get a Hamiltonian, because if you know the P square, you know the Hamiltonian, from some scattering of some material. If you have some chemistry, so you're doing chemistry, you're doing some scattering of some material, you want to know the Hamiltonian of the interaction, then you can read it off from the angle. And that was nice, and it's something that we use. This is from the 50s. And in fact, it's in Landau, of course, Landau Lifshitz. The very compact book on mechanics has this, classical mechanics, yeah. Okay, so I need to speed up. So what happens now is that I have to do the integral of this, and this is the unbound case. What about the bound case? It's the same thing. The difference that FNLs are the same. As long as the theory is local, they will be the same, but the calculation now is for a bound state. So I had to analytically continue these guys to bound. That's one of the catches. Remember, this depends on the binding energy. We go from positive binding energy to negative binding energy. That's the first thing. The same thing we do in Hamiltonian mechanics. You simply reverse the E, you make it now less than M. What does that change? It changes when you do the integral, the zeros of this function that gives me this change. Now the integral goes between R minus and R plus. This guy now is bound, so the PR equals 0 has two solutions, and then you have the two solutions. Whereas here, you go to infinity and you only have one solution. But what we realize is like you're doing the same integral. For the radial action, you integrate this. For the bound case, for the radial action of the unbound case, you integrate this. The only difference are the endpoints. So if I can loop around infinity, somehow, then I can relate this to this. And that's essentially what we did. We didn't do it this way, but it's totally equivalent. We did it for this guy because it's the observable. You don't measure the radial action. If you take a d by dj of this, then you see you get 1 over square root of this thing times 2j upstairs. So it's the same thing now. You're integrating the same thing again with different points. And the derivative picks up a sign, because if I do j minus j, because the derivative is a j upstairs, this flips sign. And that sign is important. That's the only difference. What happens to the object? After I take a derivative of g, if there is some parity with respect to g, it will be the opposite parity after I take a derivative. Because I take the derivative here, this j minus j is invariant, but if I take the derivative, I get a j upstairs, j minus j is not invariant. It picks a sign, right? And that's why when I found this analytic continuation, you will see there are relative signs related to the parity, and the g has to do with how the observable depends on g. So what's the catch here? The catch is that I need to relate these guys to these guys. And how can you see that? Is by looking at the zeros. For example, in the simplest case. The simplest case is very educational, and after you see the simplest case, using this formula in a PM expansion, because I'm going to look for the zeros of the momentum, is that I realize how to relate the bound and unbound case as well. Because the chi's are the f's, and those f's are essentially the solution to the problem. The chi's and the f's are basically exchangeable. These are, it's very interesting because these are gauge invariant, even though they enter in a gauge-dependent object. So there is some kind of notion of a charge associated with these f's that come from the angle. Also, in the amplitude business, if you go to the Hamiltonian, there is a Fourier transform of an amplitude, which in principle is gauge invariant. So there is some kind of isotropic gauge fixing, which makes this in a gauge invariant way, because in some sense, I think this you can show that if this guy takes this form, then the form of the isotropic gauge is unique. Sorry? No, I computed chi, and from the chi's I get the f's. And then if you want, you're done, because with this I can compute anything. I can compute the angle, obviously, but I analytically continue and compute the radial action. And this can be done also by the formation of the contour, and this has been done, and it's a complicated function. You can do that. But what we realized, first, by doing the integrals explicitly, and PM expanding, and later, through this very simple observation, that the scattering angle, if you do J plus minus J, is the periastrum advance. And this is the B2B dictionary. And this periastrum advance, because it's the derivative of J of this function now, of the IR, I integrate in J back, and then I recover the IR from here. And then all derivatives with respect to J, but also with respect to the energy, that gives me the period to period, the periastrum to periastrum period, and also relative with respect to the redshift, the masses, that gives me the redshift. Everything comes out from derivatives of this guy. So B2B tells me that if I know the angle, I know everything. And we can do this for a spin as well, for parallel spins, at least. And spin orbit, because spin orbit is like a parallel spin, but because all you need is a coefficient of the L dot S term, so you can get it from the parallel case. But the SS, it becomes more complicated. If it's not parallel, I don't know how to do this. But if it's parallel, I know exactly how to do this B2B map, and that means that if I know the angle, I know the radial action, I know all the observables. And that's what I was telling you. If I knew all the observables, like the binding energy, and then I do the same here, because I'm also going to find very similar relations for the energy. I'm going to find that the delta E is going to have a minus sign, but it's going to be the same, delta E. This is going to be hyperbolic, this is going to be elliptic. Then I can do the same that I told you there. Everything will boil down to relating observables from unbound to bound, as long as this formula is valid. And this formula is valid with logarithms too. I can put logs here and it works the same way. But the problem is that if this is not local, then this integral is not the same. These guys are not the same now. The guy that I put here and the guy that I put here is not the same. Because first I find an effective Hamiltonian that is local, but the coefficient of the F4 of the non-local part, not the log will be universal, but there will be a coefficient there that will be very different here than here. And when I do all of this, doesn't work. And that's why we need to remove it. And then it all goes. And then you just add what you're missing by hand. By adding by hand the part which is the non-local part is much easier than the local. The local is always the hard part. The hard part is to do all these potentials. The non-local parts, which are the far zone calculations, those we understand much better. Well, modulo memory terms that now are a little subtle. At least for the tail parts, those we control to all orders. The leading tails we can calculate to very high post-Newtonian order. We know exactly how they look like, which means we can do this non-local part explicitly to very high post-Newtonian order. In fact, Donato and Thibaut and Andrea, they did this up to 6 PN, but with the knowledge of the 4 PN flux, we can get this to 8 PN, which for all practical purposes solves the problem, which means we just need to add to that something which is known to 8 post-Newtonian orders, and forget it, that's done. So getting the local is the hardest part. So how do we relate? And since I don't have time, let me just give you a basic idea. So let's look at the F1 theory. The F1 theory is like Newton. So how would this work in Newton? And then you have here a PR square. Here I have solved this the F absorb the P infinity. So sometimes we call these Fs because they're easy to write this. But if I multiply this by F, I get P's. So here, Pn is P infinity square Fn. P infinity. And sometimes we even absorb the Gm to the n as well, and so we can get just the 1 over r, which is what I'm doing here, just to simplify my notation. So this will be, and then you have the P infinity, which is just the energy after a factor of 2, but I'm not going to put constants. It's just the trivial version of this, and there's a V squared, it's twice the energy at infinity, right? That would be this part, and there's a 1 over r, and that's the G squared, right? It's the first part, right? And then we look at the zeros. And then you look at the zeros of this, and there will be different zeros. For example, if we are now looking at the positive case, then you have minus P1 plus minus P1 squared plus 4e G squared over 2e. And the whole point is that the solutions that you're going to need will depend on the signs of first, if whether it's positive energy or negative energy. You're going to have the two solutions that you need. Well, plus is the one that I need for this guy. So our mean will pick the plus sign and not the minus sign, because the is positive. The other solution will be negative. I just want to do this quickly because I don't have time, because then you see when you flip the sign of the energy that you can get both now, because then you flip in here and then you can either go one way or the other. This flip sign, so you get plus, and then minus plus something smaller, it gives you the two solutions. Do the exercise of taking the goes to 0 plus limit and goes to 0 minus limit, which is the hyperbole. And then you will see that they are mean and they are minus of this problem. They basically go into each other. The only difference, one is positive E, the other one is negative E. So you can show very easily that the R mean of J is the R minus of J, just that this is positive, this is negative. The problem is, how do you get the R plus? And that comes from flipping this sign, because that's the other root. But notice that even though naively, right, if you look at the problem, this other solution is at infinity, that you can easily see, because when you do the expansion here, you get plus and minus, one of them cancels, and then you get the small solution. When they add up, you get 1 over e that goes to infinity, so that's the other solution. This you can do by yourself. It's very simple. Find the roots and see that one of them goes to infinity. Here. The one that survives is the one that we want. So the R mean of the scattering, as you start deforming the scattering into the bound case, will go into this solution. The point is, how do you get this solution that starts at infinity? Right? When you start analytically continue here, this one starts from infinity and it starts coming back to some value. And where does that come back from? From here. It's the roots of the same solution. It's the roots of the same function. Roots. Now here we do a trick, which is we pull the j out. So you're going to get j squared, and then here you're going to get a j in here. So you're going to get something plus minus j, something divided by something. We just pull this out. And then you notice that if you start with one guy, how do you get the other sign? By going j to minus j. So you are analytically continuing in this j, and then you get the other root. It's r minus, or r mean, of minus j of E negative. Now, we don't know how to write these solutions in general. It's complicated. But this representation of Firsoff gives us a way, because the R mean comes exactly from here, from the PR equals 0. So we put PR equals 0, then you have an R mean representation. So we have a way to write exactly the solution, the one that we want. It's very specific polynomials. There are no solutions to these polynomials in general, but this type of polynomials that have this form, Firsoff found the solution in terms of an integral, obviously. It's an integrated solution. But that we can use to do this map and show that it works to all orders. In the PM sense. Now, recently, people have realized, Martin and also Ricardo, Gonzo, I realized that I can do also E minus E, the eccentricity. It will be the same. Because this I'm going to use through here to match the fluxes. They realize that it's a much more interesting structure because they look at Kerr, for example, and they also found the orbits in Kerr can be mapped, the solutions, which is very nice. There is also an analytic solution. So there's a lot of structure here that goes beyond just PM. We did it just in PM. But now that you know that, that means that's very easy now to loop around infinity. I just go J minus J. The derivative picks a sign, and that's what I need to put plus for these guys. The energy is an integral of a flux between the same points. I do the same thing, but I don't pick a sign, so then I get minus. It's a very simple exercise now that you know how to relate the endpoints, and that the function is the same, that you can relate everything. And if you relate everything, you're done. You can construct the radial action. You can construct everything. And therefore, the radial action will be just a function. And these are even, right? Just the even chi's are going to contribute because it's chi plus minus j. So the 1 p.m., the 2 p.m. enters, the 3 p.m. does not, and so on. So it's 1 over j to the 2n expansion, which is the first one, for example, gives me the, if I go to the chi2 angle that I showed you the other day, that gives you this thing, and I go to the periastrum advance, then I get something proportional to this, and this then predicts all the Pn orders, and we check up to 5 Pn even, that this beautiful formula fixes all the 1 over j squared leading coefficient part of the periastrum just by computing the radial action. And you can compute the binding energy from there and so on. So this is beautiful. Unfortunately, it fails because of the local, non-local, but now we know that we just need to subtract this part, and then we can do this for the local part. Yes? The 2 p.m. is g squared. That's the 2 p.m. angle. These are all j squared coefficients. G squared. There is no 1 over r piece. And this is great. We can do this without sweating. I computed the angle already. I know what the periastrum is. I computed the flux of energy for hyperbolic. I get the elliptic. How do I get the elliptic? Well, it's the same thing. The integral of the flux dt becomes dr over r dot. This r dot is related to the Hamiltonian, which is itself a function of r squared and p squared. P squared is a function of this guy, so it's j squared, so it doesn't flip sign. So all the sign flips will come how the flux behave, because now that integral in r, we go between r min and infinity, or between r plus and r minus. And again, I can relate the endpoints, so I can flip around, loop around infinity, and I can relate, as I wrote over there, the energy in one case and the other. And it's very nice. You can do this. It's in our paper. You can do this and check that if you compute the hyperbolic case, which is actually much harder, because you get these cosines of 1 over minus e. But then when you do the e minus e, this plus this goes into pi. So all these cosines become pi in elliptic, and they're the same coefficients, literally. The dE of, I don't know why nobody ever realized this. The dE coefficients of hyperbolic and the E coefficients of elliptic is just this analytic continuation. And the same with the periastrum. What someone doing post-Newtonian would have even realized. We even did the PM version, but that the angle and the periastron were all the same coefficients, the even coefficients. Because the angle also gets odd numbers, and the periastron does not. So it's the even numbers of the angle, and it's because of this analytic continuation, which is, by the way, how we figured it out. We first did this the hard way, and we realized they were the same. And then I was running behind my kids on the beach, and I started thinking, oh, wait, I can loop around. And then I realized that this, because we also found that these guys are connected together with Gregor Kalling. And then I realized I could do this, and then everything was fine. Everything closed beautifully. And if it wasn't for this non-local piece, this would be the end of the story. You give me an angle, I give you an observable, I compute the full radial action. You give me the flux, I compute the flux for bound, and I compute the waveforms. And I would have never have to compute anything else. The non-local terms is what made this life a little bit more interesting. And I'm going to stop here. As I was saying over here, this is understood now at 4 p.m. Non-spin, this has been done. Spin, we haven't yet subtracted this. 5 p.m., the full angle, conservative only, 1 SF, without tail of tails is none. But there's a lot of work to do here. To include 2 SF, to include dissipative, to subtract the non-local part, and to include the tail of tail. There's a lot of things that miss. The problem is that these integrals are very hard, not because the integrals are hard, the boundary conditions are easier. What is hard is to go from the integrand to those masters that I wrote. That's the hard part. That's where this IBP reduction story becomes subtle. And that's where we got stuck, and also other people. But then one guy figured it out. The guy who developed Kira, I forgot his name now. And he basically enabled the group in Humboldt, led by Jan Plewka and collaborators, to do this. Because doing the integrand is easy, reducing to master is hard, solving this is not too difficult. And that's why we decided to also do this first, because we were stuck here for a while. But since this had to be done, now we were the first to actually have a 4 p.m. result, which is useful, which is an honest PM resum bound local in time effective theory, Hamiltonian, whatever you want, which we couldn't do before. Before we had all this pollution of the non-local part, so we had a hyperbolic Hamiltonian, but it was useless for the bound case. It didn't even reproduce the 4 p.m. energy, so it's completely useless. Now we not only reproduce the energy, we get even more, way more terms. So now we start understanding. A PM version of this would be great, but it's much, much harder. And I need to stop here. Thank you very much.